straightforwardly set.
Nice. Good morning, everyone. How's the team? Software leader. Let's get this act. Let's get our act together here. Let's see. Why is that so weird? Okay. All right. Let's see how this is. Cool. Well, good morning. Let's warm up a little bit here with something that we sort of ran out of time to talk about yesterday, which is this sort of a 3.9 mathematicians are amazing about coming up with statements like this. Logarithmic differentiation. How did I get in this class? But it's kind of cool. This is kind of a cool trick. So let's just look at a couple examples and see if we can't understand the beauty of this. And you have a question in your assignment like this, and you have a question on your quiz, your take-home quiz, kind of like this too. Let's see, let's make that a 3. Let's make this a 6. So all numbers are different. So you already know how to do that. That is the quotient rule. And that's great. It works awesome. But one of the things I want you to take away from yesterday is just the fact that, you know, now that we understand that you can just take the derivative of both sides of an equation, that's how you take a derivative, or that's one way to take a derivative. And the fact that you can mess with stuff, that was a big part of yesterday, depending on what extent you took it all in. We can mess with stuff like before you take the derivative of both sides. And this is kind of cool. Well, if you still know some of the properties of logarithms. But just for instance, before we take the derivative, let's just make a note about that. Before we take the derivative, let's do some algebra. So for instance, if we took the natural log, let's take the natural log of both sides. That seems really dumb. So if I did that, I'd have the natural log of y equals the natural log of all of this gobbledygook. Why would somebody do that? Because that's just worse. Now we still have to take the derivative, and yet we have all of this junk. But remember some of the properties of natural logarithms. Like if you have the natural log of junk divided by junk, that's actually the same as the natural log of junk minus junk. Is that back in the cobwebs of your mind? Just a quick reminder, but in other words, if you have and you could type this in your calculator really quick, just if you decided you wanted to, because it's very exciting. Like natural log of 5, 15 divided by 3. So natural log of 5 is a decimal, and if you took the natural log of 15 minus the natural log of 3, you get the same answer as the natural log of 5. I mean, that's the property that I'm reminding you of logarithms. Remember, logarithms are exponents, and when you divide, don't you subtract? In other words, you have x to the 7th divided by x to the 3rd, don't you subtract those exponents? Division and exponents are related, and that's all I'm reminding you of here. That was one of the properties of how exponents worked. And then the thing that's even more lovely about this is the fact that if you have natural log of x minus 3 to the 5th, that 5 can come down front and become the natural log of just x minus 3. And the 6 can come down front. So that's just this. Now what's really cool is now you don't have exponents anymore, which exponents are chain rule, right? If I just look alone at this statement right here and think about taking the derivative of that, that's junk to the 6th power. So I'd have to bring the 6 down and then take the derivative of what's inside. I don't have that. I don't have division anymore. I don't have the quotient rule. So in a sense, quotient rule is gone. A lot of stuff is gone. Well, if you're comfortable taking the derivative of natural log. And so this is just another method, logarithmic differentiation. So if you take the logarithm of both sides, maybe your life gets a little easier. I don't look at this so much as, let's try to get this done as fast as possible, or let's get this done in the easiest way we possibly can. It's more just, hey, I can think now. I can reason. If I want to do algebra to an equation, before I take the derivative of both sides, I can. And when we're just learning this, like maybe that'll make my life easier, maybe it'll make it harder, but I don't really care. It's just that I can think. I mean, if you try to learn math by steps, what are the steps to do this problem? Well, every problem has different steps, and so you're just never going to learn math. So the idea that I can think, I can do stuff, I can do things to an equation if I want to. And even clear back here, like for instance, if you multiplied both sides by 2x minus 4 to the 6th, then now you have product rule instead of quotient rule. Just the fact that I can do things, I can be creative, I can do the problem more than one way. So let's see what results. Now let's take the derivative. Okay, so if I did that, the natural log of junk, the derivative of natural log of y is 1 over y times the derivative of the junk. The derivative of, well, the 5 comes along for the ride. The derivative of natural log of junk is 1 over the junk times the derivative of the junk. Notice the junk there is x minus 3 and the derivative of x minus 3 is 1. I'll go ahead and write the 1 in there, but you don't really need to. Then the 6 comes along for the ride. The derivative of natural log of junk is 1 over the junk times the derivative of the junk. Since 2x minus 4, the derivative of 2x minus 4 is 2. So, I don't know, is that easier? Again, you're kind of done in the sense that you now have y prime. Well, I should solve that at least a little bit, I guess. So for instance, if I multiplied both sides by y, and then I guess I could multiply 5 into that x minus 3 and 6 times 2 into that 2x minus 4. Again, you're done. And there's another element of you're done. Since y was actually equal to all of this gobbledygook up here, if you wanted to, could you replace y down here with that x business up there? Yeah, just for the sake of your practice in algebra, let's do it and see if let's see if that was worth doing. I'm not really sure. In other words, I sort of want to write a question here. Am I done? Like, should I stop right there? Should I, does it make sense to try to add these two fractions together? Remember, the goal of this is not just to find the derivative, but to say, what's the derivative when x is 2? And so, should I stop now? I don't know. Just be good at algebra. So I mean, that for your skill as an algebra student, well, let's just move on a little bit and see if this is worth doing. And I genuinely don't know. Like, is this going to pay off? I don't know. Let's see. So if I did do that, I could say that y prime was equal to, if I replace y with x minus 3 to the 5th over 2x minus 4 to the 6th, and it's still multiplied by all that junk inside. Maybe you see that I could divide 2 from this equation on the right. Since there's a 12, a 2, and a 4, I could take 2 away from all of them. Maybe that makes my life easier. So, you know, are there advantages to what we have there? Well, I guess one advantage is if I said if I need to know the slope at x is 6, well, now you only have x in it and you don't have y. But it's uglier, so I don't know. And again, I'm wondering out loud because I truly don't know. Should I distribute this inside? I mean, is that a good idea? That's kind of seems like a bad idea, but again, let's learn some algebra. So if I did distribute that inside, I'd have a 5 on top and an x minus 3 to the 5th on top, and I'd have a x minus 3 on the bottom and a 2x minus 4 to the 6th. So that's just distributing it to the first term, and then I get to do this all over again. And I guess on the bottom I have 2x minus 4 to the 6th times 2x minus 4, that'd be 2x minus 4 to the 7th. And I guess one of these cancels here since there's one on the bottom and one on the top. So let's see, where am I? 5x3, x minus 3 to the 4th over 2x minus 4 to the 6th. What do you think? Are we done now? Should I stop? Well, we almost have a common denominator. Remember, you can't add fractions without a common denominator. So if I multiplied this one top and bottom by 2x minus 4, then I'd have 2x minus 4 to the 7th on bottom. But I'd have another 2x minus 4 on the top. But at least I have a common denominator. Whew, notice that doesn't look so great. Again, I'm just wandering randomly here. That answer, I'm looking back thinking, yeah, I think maybe I was done, like clear back at the start. Maybe I was done clear back there because it just got worse. Well, I'm in this far. Let's keep going. What if I factored out, since both of these terms have an x minus 3 to the 4th in it, what if I took that out? Which sort of seems counterproductive. It's almost like I'm going back to what I had before. Then that would leave 5 times 2x minus 4, which is actually 10x minus 20, since this x minus 3 to the 4th is outside, then I just have that left. And then 4 of these took off, so now there's just an x minus 3 left. And if I multiplied that x minus 3 by 12, that would be minus 12x plus 36 all over 2x minus 4 to the 7th. And then I can actually clean up this parenthesis a little bit. So I don't know, x minus 3 to the 4th, and then 10x minus 12x. 36 and negative 20 is 16. 10x minus 12x is minus 2x. No, that's arguably, again, I sort of asked the question, done? I don't know. I don't have a strong opinion about that. Obviously, all that stuff I just did and read is really dangerous. Like even if, like me, you know algebra really well, you still might have made a math mistake there. So I'm not even sure I didn't screw up in all of that. But notice you got to be awesome at the distributive law. The only advantage to this last answer, I guess, is as I said before, you only have one x in it. You don't have any y's. So I don't know. That's just cool. Is it easier? I mean, if you go back to the start, would you say that's just all terrible? Remember, as I said, we could have quit right there. I think there's an argument that made that problem easier without all the simplification I tried to do. I could have made it easier. Maybe I get all screwed up if I say that's a quotient rule problem inside a chain rule and so forth. It's like, oh man, I don't know. Maybe that made my life easier, but of course I had to know the properties of logarithms to pull that off.
I think the ease of that equation or the ease of that answer is more defined by what your information is given. If you're only given an x, then it might be easier with the second
That's a good
equation.
point. Yeah,
But if you're given an xy, then
that's a good point. If you're told find the slope at 6.2, the 0.62 or something like that, then maybe, yeah. So anyway, have some creativity. I don't see this as a huge concept or something that's essential. However, let me show you this one other problem. So we'll just say that was kind of example number one. This one, it's actually not optional. And again, this is just mathematicians being dorks. But what if I said, what is the derivative of the sine of x all raised to the x power? You actually can't do this problem. And again, I don't think you've practiced enough to be convinced of that. But remember, we had a formula for, well, not sine of x, but what if it was like 5 to the x? You can handle it from yesterday if it's 5 to the x power, because remember that base had to be a number. You can handle that. Or you could handle it if this is a sine of x, but this up here needs to be like a number. You can handle that. But if they're both x's, you're actually in trouble. Like nothing you know allows you to do that problem. You're actually in deep trouble here. So you can't even do this question without logarithmic differentiation. So you can't handle that. But again, that's what logarithms do. So again, before I try to take the derivative, if I take the natural log, and could I take the log of both sides? Yes, but remember the derivative of natural log is a little simpler than log was. So if I take the log of both sides, natural log of both sides, again, one of those properties is that x on top up there, this x can lie down front. In which case, now I don't have an exponential, kind of a weird exponential problem anymore. So natural log of y equals x times the natural log of the sine of x. Now I can do it. So I have to, just for the sake of practice, notice that this is a multiplication. So I'm going to need to do the product rule. So I say, okay, now I sort of take the derivative, both sides. So the derivative of natural log of y is, and the derivative of natural log of junk is 1 over the junk times the derivative of the junk. Product rule says the derivative of x, which is 1 times the other side left alone, plus the x left alone times the derivative of natural log of sine of x. Maybe you think, oh, derivative of natural log of sine of x. What is that? Well, derivative of natural log of junk is 1 over the junk times the derivative of the junk. It's no different than what we did on the other side. Let me make myself a little room here. Derivative of natural log of sine of x is 1 over the sine of x times the derivative of sine of x, which is cosine of x. Coincidentally, we did that question yesterday. So let's see, I'm a little confused. Let's clean this mess up. So I've got 1 over y times y prime equals 1 times natural log of sine of x. It's really just natural log of sine of x. Plus x times cosine over sine. Cosine over sine is cotangent, so I guess I could just say x cotangent, just to make it look a little nicer. And then multiply both sides by y. So y prime is equal to y times all that junk right there. So let's copy it. Again, if you write that, you might be correct in your mind, but that isn't true. What does the y get multiplied by? Should be multiplied by everything. So I don't know what I would do on a test if you told me that answer, but it's pretty important you have those parentheses. Again, I have the same question as before. Should I just stop now? Am I done? Well, I mean, I could replace y. Remember back at the start of this, y was the sine of x to the times to the x power, so I could replace that, I guess. Again, isn't that just insane? Like that would even be a recipe for the slope of our original problem. It's just almost hard to believe. But again, that's just interesting. This is just, as I've said a number of times, it's just mathematicians being mathematicians saying, can we take the derivative of anything? The original problem was actually fairly simple looking, but you can't even do this question without getting logarithms involved, because you can't have x's to the power of x. That fits no pattern of anything we ever saw. And so because that is just such a confusing process, you get, a ridiculous answer to this question, but there isn't anything simpler. Like, that's as simple as it gets. It's just weird. Again, I'll give you an early heads up. This is probably not something I'm going to stick on a test. I think it belongs in a couple of homework questions, which it is. Maybe it belongs in the take-home quiz, just to see if you can do it and so forth. But this feels like a pretty obscure concept. How's your brain? Did it overheat there? You're right. Looking for smoke coming out of ears. I don't see any. I wonder if smoke came out of my ears when I learned this. I can't remember. I survived. I don't know. Well, there's a freebie. Okay. So now we're going to kind of go toward, we're starting to kind of cruise toward the end of chapter 3 now, which is really kind of comes down to applications of this stuff. Because you can see we're already looking at, this last problem we just did is a pretty crazy question. As I warned you, at the start of this class, taking a derivative tells you the slope, and then mathematicians, of course, say, well, let's try to take the derivative of everything under the sun. Well, sine of x to the x power is a pretty ridiculous equation. So we're at the place of we've now taken the derivative of everything under the sun. But let's take a look at something kind of strange. If you have your note sheet that I gave you, you might want to pull it out, because I'm about to show you the derivative of inverse trig functions. That's what 3.10 is about. Inverse trig expressions. Let me try to get you going on this in a way that starts to help you understand what you can do with this. And so let's take a kid with a rocket on the ground. That's a rocket. I don't even have to tell you, it's such a good drawing. You already know it's a rocket. That's not a mushroom. What are you talking about? So that rocket's going to take off up in the air, and we'll put the kid 6 feet away from the rocket. I don't know why I'm calling it a kid. Like, I would still send a rocket off, and rockets are awesome. Blowing stuff up, awesome. So you might be the observer over here on the ground. And so does it make sense? We'll just keep it simple for now. It doesn't have to take off at a 90-degree angle. You could send it off at a weird angle. But if I send it off at 90 degrees, can you see that, if you will, changing? And what I want you to think about is variables versus numbers. So you have this right triangle here, and let's say this is 13 feet. Why can I not say that's 13 feet? Why is 6 feet okay, 13 feet not okay? Why does that not work in this situation? There's the rocket up there. I'm asking you to read my mind here a little bit, but why is that impossible?
Is it because you have to use, never mind. I was gonna say is because you have to use tangent to find the angle, but
The reason is if that's 13 feet, then what's the rocket doing?
Stalled out.
It's floating in midair. Like, as I mentioned before, calculus is the mathematics of motion. So can you say, what's happening? Could I ask the question, and this is, mathematicians do this kind of thing. Could you say, okay, at one point the rocket is 13 feet in the air, and maybe that's an interesting question because that's where it, hit the house, hit the roof of the house or something, whatever, hit the ceiling or something like that. And so, you say, hey, could you set up tangent and figure out what the angle it was? Like, what's the angle when the rocket hit the roof? It's not that that's impossible, but the reality is the rocket just keeps going. And so I guess what I want to get across is it's kind of a better thing. If you're just going to let this fly up in the air, then really it makes more sense to call that a variable. Whereas if the rocket took off from here and you stood 6 feet away from it, that 6 feet isn't changing. But that height there is changing. And so we don't want the rocket to freeze in the air. We want to let it fly. And so that's got to be h. It's got to be a variable because the rocket is cruising up in the air. What about the hypotenuse over there? Is that a constant or is that a variable? Well, the rocket's changing length. That's going to have to be a variable too. I'll call that. What about this angle right down here?
That's going to be a variable.
So this angle over here, basically theta, can you see theta is getting bigger and bigger and bigger as the rocket gets higher? This angle up here, I'll call it alpha, is getting smaller and smaller and smaller. This angle down here, though, is a constant, isn't it? I'll make this a little bigger. Like, isn't that stuck at 90 degrees? So the triangle's got 3 angles and 3 sides. And one angle and one side are constants in this problem, but all the other ones are going to be changing as the rocket sort of flies higher and higher and higher. Does that concept make sense? And so this is how calculus gets involved. Now I'm going to simplify this a little bit, but that logic will help you think about this a little bit later. And so what I'm interested in this problem is, and I guess I want to know, can you interpret this? Can you interpret this statement? I am interested because I'm a nerd kid. I'm interested in d theta dh. What is that person interested in? Again, this is just something that a person that knows calculus can consider that other people can't consider.
the derivative in respect to the height,
Yeah,
or sorry, with respect to theta.
it's really asking, that's exactly right. It's really saying, how is theta changing? How theta changes depends on how h changes. So let's pretend, for instance, the rocket is rising really slowly. It doesn't really make sense that a rocket would rise really slow, but think of it as a hot air balloon. Hot air balloon is rising really slowly. Does it make sense the angle that it takes to kind of look up and see it doesn't change very fast? So if H is changing really slowly, then theta is also changing really slowly. But if the rocket is just taking off super quickly, then does it make sense the angle changed super quickly too? Does it make sense they're dependent on each other? Now, again, this just looks like a kid who has a rocket that's doing math instead of having fun trying to shoot a bird with it or whatever. But there's a practical side to this, and that is this. What if that's not just a kid with a rocket, but what if that's a cameraman over there and they're filming a launch to the moon? And so you're trying to, and you've watched golf perhaps on TV, ever watched them try to film the ball? It's like they hit it and then the ball's flying through the air and they're trying to like follow the ball. Have you ever tried to film something moving with your cell phone? Like it's all wobbly and you can't get it in focus. So in a sense, this is the camera person filming it, the rocket launches, and they're trying to keep that rocket in their field of view. And so they're having to turn the rocket. They're having to change theta. They're having to change the angle that they're leaning back. Maybe they're just holding it on a tripod or something. They're having to change the angle of that to keep the rocket in focus. And, how cool would it be if you could even have a machine do that? Based on the speed of the rocket, if you could have a machine keep track of the speed, and then it's just perfectly focused on it the whole time. And that's kind of what I'm getting at here. It's a playful question when it's a kid with a rocket, but it doesn't have to be playful. So, well, you can't take the derivative of something if you don't have an equation. And if you want d theta dh, then you've got to have an equation that's got thetas and h's in it. Is there a way to, what equation has thetas and h's in it? This is what you got to be able to build for yourself. It's not Pythagorean theorem. Pythagorean theorem could get h6 and L involved. So I could say 6 squared plus h squared equals L squared. That gets h involved, but it gets a letter involved I don't want. And it doesn't get theta involved. What equation gets theta and h involved for sure?
The tangent of theta equals h over 6.
Nice. We need an equation. In order to go find d theta dh, we need an equation with thetas and h's in it. Does that logic make sense? We need an equation with theta and h. Correct, tangent. So I can say the tangent of theta equals h over 6. Now you can take its derivative. Or couldn't you do this? So what you understand more recently is you could take the derivative of that right now. Or you could solve for theta first by taking the inverse tangent of both sides. So at some point in here, because again, we're not just interested in, what theta is. As I said, if h is 13, you could solve for theta and find out what angle it was at. That's a static problem. The rocket's not moving, but this person is concerned about speed. They're interested in how the angle's changing. How fast do I have to rotate my neck or the tripod? But the point is what you do with calculus is you find the equation yourself that relates these things, and then you take the derivative. And I don't know about you, but I'd rather take the derivative of this one because I know what the derivative of tangent is. But when I come down here, I think I don't know what the derivative of inverse tangent is. Like, so let's just take a look at those two and just think out loud for a second here. Let's kind of look at both of those. And so let's take the derivative of one. So the derivative of tangent of junk. And again, you don't need to know anything new. Like you've now practiced derivatives. And so you should be able to do that right now. As a matter of fact, I'm going to shut up and give you a second to see if you can do it. And it's also a little confusing because it doesn't have just y's and x's. But do you agree that first question is, well, it's not solve for theta. This is an implicit differentiation problem. And because it's d theta dh, we're looking for theta prime. That's kind of our y value. Can you take the derivative of that first expression and find d theta dh? Just going to give you a few seconds to think about it so we don't run out of time. Well, the derivative of tangent of theta, the derivative of tangent of junk is secant squared of junk. So I took the derivative of that side. What's this person doing wrong? If you stop right there, what did you do wrong?
Well, would you have to multiply by theta prime?
Right. The derivative of tangent of junk is secant squared of junk times the derivative of the junk, chain rule. So times the derivative of theta. So if we're looking for the derivative with respect to h, then the derivative of theta is not 1 because theta is not h. So you could either say times theta prime or times, well, d theta dh. In other words, what we're really doing up here is calling this theta prime. So I got to say times theta prime. What about the other side? Well, the other side is h. And since I'm taking the derivative with respect to h, then the derivative of h isn't so hard. Notice that's really just 1/6 times h, and the derivative of h is 1, so that's really just 1/6 over there. Now, you're more than welcome to say it's 1/6 times h prime, except for we know h prime because we're taking the derivative with respect to h. H prime is 1. Theta prime is not 1, but h is 1. Again, that's not,
So,
it's not awesome.
So basically, like in the implicit differentiation assignment, if it had been asking to find the derivative of x with respect to y instead of y with respect to x, it would just been the opposite of what we were doing and finding x prime instead of y prime, correct?
And this, do you understand that this is causation? In other words, the person asking this question is saying, I wonder what effect the speed of the rocket, h, how fast h is changing, I wonder what effect that'll have on theta. You see the cause there? But a person could go the other way and say, I wonder what effect the angle changing would have on the rocket. Now that doesn't make sense in this case. But yeah, if we were asking the question, what's dh d theta, then this would have been 1 and this would have been h prime.
That makes sense. This is neat. I was as I was going through the implicit differentiation as I started going getting towards the end, it started just becoming really smooth with how everything was working out, and I was like, oh, I finally started to understand this.
Yeah, and I want to highlight, I've said this a little bit before, but it's like, you've got to practice this a lot. I can show you, but you really need to practice this a ton. You got to carve out some time and do a ton of questions so that you can kind of get in the swing of it. If you did that, then probably this isn't losing you because I'm using totally different letters. Okay, well, we got theta prime now. All we're going to do is divide by secant squared. So I have 1/6 times secant squared. That's extremely nice though, because secant is 1/cosine, and secant's weird, like I don't have a secant button. Well, it's 1/cosine, so actually I could switch that with 1/cosine, and that end up with cosine squared of theta over 6. So now I have how it's changing dependent on what h is. So I have a formula for it. And remember, that's the same thing as d theta dh.
So for this, we would have to solve for h to even, or solve for theta to even use it in the equation, since we lost our h in the derivative. Right?
Yeah, that's right. The h kind of went away in the derivative. And so
I guess that happens in implicit stuff sometimes.
Yep. So let's just do a couple really quick. Do you have a sense of this? Like if you were watching, let's just say it was, like a full rocket, like launching to the moon, and you were lucky enough to be at Cape Canaveral and you're watching it. what happens like in the beginning, you're watching it go up and the rocket is traveling up at the same speed? Is your neck moving faster in the beginning and then slower later on? Or is it the other way around? Does it move really slow in the beginning and then it really takes off quickly? Do you understand that angle's not changing speeds at the same time? Think about a car traveling by. Maybe this is easy. You're standing by the road. Here comes a bus. The bus is traveling. Does it make sense when it's a long ways away? You don't even have to turn your neck at all. Like it's coming towards you, but you hardly even have to turn your neck. Yet when it gets in front of you, don't you have to, your neck just has to rip by. It totally changes really quickly. The angle at which your head is turned has to change really fast as it passes right in front of you. So let's use this just to kind of make sense of this. And so let's say what happens, well, when h is, say, 2 feet. And I didn't look up to see who said this. Was it Logan? I can't remember, but notice our recipe calls for theta. It doesn't call for h. And so like, what do I do with 2 feet? I can't put it in there. So, well, we knew that tangent of theta was equal to h over 6. And so if h is 2, then I could say the inverse tangent but we could do something even better. So inverse tangent of 2 over 6 and we'd get an answer, but we could do something even better. Take a look at this equation right here, and this will help you with something I'm going to show you in just a minute. If this distance is 6 and this distance is 2, and you need to know the cosine of theta, can you know cosine of theta without ever knowing what the angle is? You don't need to know theta, you need to know the cosine of theta. What's cosine? SOHCAHTOA, what's cosine?
Adjacent over hypotenuse.
It's adjacent over hypotenuse. Well, I don't know the hypotenuse, but if I know 2 and 6, can I figure the hypotenuse out? So 6 squared is 36, 2 squared is 4, 36 and 4 is 40. So wouldn't that be the square root of 40? So actually the cosine of theta is 6 over the square root of 40. Like I don't even have to go figure out what theta is, and I can find that. Isn't that kind of cool? Saves me some time and actually makes it perfect. So that means d theta dh being cosine squared theta over 6. Well, if cosine squared is, well, we know cosine now is 6 over the square root of 40. That'd be 36 over 40 if I squared both of those over 6. Let's see, that's 6 over 1. So I'm really dividing 36 over 40. I'm multiplying it by 1 over 6. Oh, okay, so one of those 6's cancel. I get 6 over 40. Or 3 over 20, or let's see, can I do this in my head? 3 over 20, that'd be 15. So this is 15/100. So this is 0.15. Anybody know what those units are? Like what the heck does that mean again? We just found d theta dh. What's the units?
Did we even specify?
Feet
No.
per radian angle, I guess.
Yeah, so the top was an angle and the bottom was h, which was feet. So I did specify the length was feet. So I guess we're working in feet. So notice the units of this would be, well, an angle per foot, but we have 2 ways of naming angles. We have radians and degrees. Which one is it? Like we never specified. So is it like whatever you want? Is it 15 degrees per foot? Or is it 15 radians per foot, 0.15? That's a super interesting question. But watch this. This is fascinating. I don't know about you, but I like degrees and I don't like radians because I think in degrees. But let's look back here a little bit at units. Would you agree this 6 down here was feet? And wasn't this feet? And this was also feet? So on the top, don't the feet cancel? So there's no unit there at all. So when you get all done, the answer to this is actually feet, and then there's nothing up there. There is no unit. that makes it radians. Radians are a unitless way to measure an angle. So this is radians per degree, or sorry, radians per foot. And just out of curiosity, if you take 15.15 times 180 divided by pi, you get 8.5. So this is 8.5 degrees a foot. I don't really think in radians too well.
And now is it unitless because regardless, 2 pi is going to make a circle? Or
Yeah, and it has to do with the fact, this is why radians are so cool. We say this is the unit circle and that length is 1. It's not 1 foot, it's 1, like it's a unitless 1. Therefore, the distance around this is 2 pi, 2 times pi times radius, if the radius is 1. So that's, we're measuring it, we're measuring an angle in radians by a length is kind of what it comes down to. And it turns out that like radians are the way angles should be measured because they're the language of the universe. Like this, we didn't even choose, like this answer came out in terms of its units, it came out nothings per foot. So what do you mean the angle is nothings per foot? Well, that's what radians really are. Like we actually call it radians, but it's really unitless. It's a unitless way to measure an angle.
well, I guess it's neat because you can apply that to any unit you want after that, as long as you know how to.
Yeah. So again, I just want to give you time to kind of soak on this. So we'll say like, okay, we did it at 2 feet and we got 0.15 radian per foot. So in other words, at 2 feet, when it went up 1 foot, then our head, if you will, has to turn, well, I turned it into degrees, 8 degrees. But what happens if it's way higher than that? So let's look at a second case. This is what makes calculus, I don't know, useful. Let's choose a different color. Like what if H is, let's see, let's make it come out a little nice this time since we can. What if H is 8 feet? So we do this all over again and we say, okay, this time, I won't draw it to scale. This is 6 feet, this is 8 feet. I made this really nice because that's 10 feet. That's a 3, 4, 5 triangle. So the hypotenuse is 10 feet. So now we can say that the cosine of theta is 6 over 10. Like we don't have a square root this time. So that's kind of an unusual case. So then that means d theta dh, just like last time, is, well, cosine squared. Our recipe back here said cosine squared. So 6 over 10 squared, 36 over 100 divided by 6, which ends up to be 6 over 100, or 0.06. So 0.06 radians per foot. Slower. It's not the same. Like even though for a foot of height, every foot of height, it isn't the same. It depends where you are. A foot, if it's way up in the air and it goes a foot higher, your head hardly has to turn at all. That's what this is telling us. It's way slower. A foot way up high, and notice that isn't even very high. It's only 8 feet. If I'd went up to like 20 feet, this is on its way to nothing. And you can picture that if you're looking at a rocket and it's 1,000 feet in the air and you're looking up at it and then it goes 1,001 feet, you can't even tell that it moved. Your head hardly turns nothing. So motion is complicated. Like you want to understand motion, you want to let things move, you want to let the rocket fly, not freeze in the air someplace. Complicated.
There's actually an engineering company in Medford that builds camera systems for like tracking objects. So I think this is probably something that they would work with actually.
Yeah, this is very realistic. And not only that, the other part of this you have is the focus of the camera, because as it's flying up in the air, doesn't it get further away and you have to change the focus? So you know, having a camera that can actually handle all of that. You know, we have drones that can follow things now, and it's, yeah, I mean,
There's a lot of math in those things.
so much math, so much math and all that. And in the end, that's why you're preparing for some engineering. I mean, you're taking this class ultimately so that you can be the kind of people that make stuff like that instead of just buy it. So this is really cool stuff, and you're exactly right. It has a practical component. But now let's look at the second question. And so what I'd like to argue ultimately is, I'll rewrite it down here. Does it make sense that I don't know how to take the derivative of inverse tangent? And so that's what this section really is. But what I'd like to argue is you don't need to know this because can't you take the inverse tangent of, or take the tangent of both sides? Like you don't need to leave it that way. So again, I put this section in the category of this is just interesting to know. In other words, can I find d theta dh here? How do I, what's the derivative of inverse tangent? I know what the derivative of tangent is, it's secant squared, but what's the derivative of inverse tangent? It's kind of, wow. So there are, my point is there are functions. Theta in this case is a function of inverse tangent. And so, you know, functions like this really do exist. So, you know, what would I do in this case? And so that's really what 3.9 is about. So let's go see if we can find the derivative of all of them. And this is where I'm directing you to your note sheet. Let's see, I'm gonna look at it really quick. What's the first one? The first one is the derivative of inverse sine of x. So let's try to build that. So let's build the derivatives of the inverse trig functions. So to start with, let's do, what if y was the inverse sine of x? And you want to know what's y prime. Well, that's what I was saying before, like we don't know. So do math to it first. So do, like, take the sine of both sides. Doesn't this mean the same thing as the sine of y equals x? Doesn't that mean the same thing? Like, do that first. Now take the derivative. This is what we've been doing for the last couple of days, is staring at something we don't understand. Yesterday we stared at y equals the natural log. Let me write this again really quick. We stared at that and went, oh my gosh, what do I do? I don't know what to do. I've never seen natural log before. And so we said, well, that means the same thing as e to the y equals x. So we transformed it to this. And then we said, oh, okay, now I can take its derivative. And that's how we built the derivative of natural log. That's all we're doing here. Same exact thing. We're staring at y equals the inverse sine of x and saying, I have no idea what that's talking about. So we change it to, we transform it to something we do understand. And thanks to implicit differentiation, you say, okay, I can do that. That's really easy. What's the derivative of the sine of junk, cosine of junk, times the derivative of the junk? The derivative of x is 1. Again, because what we're really looking for is we're trying to find dy dx or y prime. That's what we're always trying to find. So there, I found it. All I have to do is divide by cosine, then I'm done. Y prime, I found it. In one sense, I want to say, done. We found it. Notice the recipe calls for y, not x. So how come my note sheet has such a weird answer to it, a weird answer in it? So we are done. That's a fine answer. There's nothing wrong with that. However, let's take a look. And I wonder, and this is kind of related to what I just did a minute ago. A minute ago, I said, hey, let's go find the tangent of theta. And I said, well, can't we draw a right triangle of this picture? Can't we draw a picture of this? And that's the question down here is the same thing. Can we write this some other way? If you will, this recipe for slope calls for y. Fine, use it. Just go get y. That's okay. But could we get it to call for x if we wanted to? And the answer is yeah. I wonder from trig, can you draw a picture of sine of y equals x. Like, what does that look like? Well, when you see sine, you should say trigonometry applies to right triangles. So this is a right triangle. True. If you're taking the sine of y and it equals x, then what does that mean the units? What does that mean the units of y are? Like, what is y? If you're taking the sine of it, what is y? I want you to tell me that. I'm asking you to read my mind here a little bit, but I'm not saying you know it, like, oh, it's feet, it's miles, it's kilometers, but it's like, what part of the
Radians.
triangle is it? If you're taking the sine of it, then what part of the triangle is it?
Opposite.
You're
The
going a little,
angle.
yeah, the angle. Like, sine is opposite over hypotenuse, but if you're taking the sine of it, then it must be an angle. Does that make sense? Triangles have sides and angles, and if you're taking the sine of it, there must be an angle. Okay. So I'm going to put it right there. I don't have to put it there. Remember, trig applies to right triangles, so it has to be a right triangle. So there's angle y. And if you take the derivative, I'm sorry, you take the sine of the angle and it spits out x, isn't sine opposite over hypotenuse? So Katoa, sine is opposite over hypotenuse. So, what are the units of these two things? The y has to be the angle, and the x has to be opposite over hypotenuse, but it's only x. How do you get a hypotenuse? Like, doesn't it have to be a fraction? Well, it is a fraction. Isn't x a fraction? X is x over 1. So if the opposite over hypotenuse is x, then wouldn't this have to be x and this have to be 1? You see what I mean when I say draw a picture of it? Again, I don't think most people leave trig understanding that. Like, if you're taking the sine of something, then it must be an angle. And the other side is the ratio of two sides in the right triangle. Now, what good does this do? Well, a second ago, didn't we say we want to know what the cosine of y is? Well, can't we know the cosine of y now that we have a right triangle? Well, kind of. Unfortunately, cosine is adjacent over hypotenuse, and this is the adjacent side, and I don't know what that is, but can't you use Pythagorean theorem to find it? Wouldn't Pythagorean theorem say that the adjacent side squared plus x squared would have to equal 1 squared? And so I would have the adjacent side squared equals 1 minus x squared, and then I would square root both sides. So the adjacent side would equal the square root of 1 minus x squared. Cool. Now I know what the cosine is. The cosine of y then, without ever knowing what the angle was, the cosine of y must be adjacent, which is the square root of 1 minus x squared over hypotenuse. Since the hypotenuse is 1, I could just say 1 minus x squared. So then I guess I could say that y prime equals 1 over the cosine of y, but I could also now say that it's equal to 1 over, well, the cosine of y we found out was the square root of 1 minus x squared. So this recipe for slope calls for x. That's why your note sheet says if, I guess I'll write it out formally, if y is equal to the inverse sine of x, then y prime equals 1 over the square root of 1 minus x squared. This is the, mathematicians would call this the theorem, the truth. Again, isn't that weird? Like, what a weird recipe for slope. If you have an inverse sine graph, then you find its slope at a point x by plugging x into that strange expression.
Would it also be y prime equals 1 over the cosine of the inverse sine of x? So taking the original equation and plugging it in for y, or is that just in this
Nice job.
situation that works out?
Nice job. Like, couldn't we also say that y prime being 1 over the cosine of y, but didn't we start out with y being the inverse sine of x? So could you say it was 1 over the cosine of, what's y? The inverse sine of x? Yep. That'd
So I
be,
guess that's kind of unsolvable, so it was easier to come to that conclusion, but not easier to use it, I guess.
well, I would say that's not
So-
true. Like, you have the button on your calculator. So if I said x is 2, couldn't you type 1 over the cosine of the inverse sine of 2? You could type that in your calculator. That's not terrible.
Okay,
It's weirder looking, but it's not terrible.
all right.
That's a great observation. Good for you. Well, a minute ago we needed tangent. Let's see if we can build tangent. So we're sitting there with y equals the inverse tangent of x, and we need to find its derivative. We need to find the derivative of that. So you start this yourself. Start this yourself. As I said, we're going to have to transform this by ultimately taking the tangent of both sides. Like, can you take the derivative of that? Can you draw a picture of the tangent of y equals x, and can you build for yourself the formula for the derivative of the inverse tangent of x? Just going to give you a second. I won't give you enough time probably, but and this is the same thing we did a minute ago. Like, that's how we did it a second ago. So the derivative of tangent of junk is secant squared of junk times the derivative of the junk. Oops. Junk is y, not theta. Secant squared of junk times the derivative of the junk. The derivative of x is just 1. And so this is not hard. Y equals 1 divided by the secant squared of y. And that's conveniently the cosine squared of y. Y prime, sorry. There it is. Done. There's one of our recipes. Y prime is the cosine squared of y. That's what we saw a second ago. But what if we didn't want the y? Like, what if we wanted it to be x again? Well, again, let's look at the right triangle that this represents. If tangent of y, tangent is right triangles, y, if you're taking the tangent of it, it's an angle. So I drew the right triangle over there at the right again. But if tangent of y is x, where does x go in that triangle? And what does it mean? Well, tangent is opposite over adjacent. So since x is x over 1, then this would be the opposite, and the 1 would go here this time. And then I could do Pythagorean theorem on those, and this time it'd be 1 plus x squared, the square root of 1 plus x squared. And so now can I identify from this triangle what the cosine of y is? Cosine of y is adjacent over hypotenuse. But we're squaring that, aren't we? So we're squaring 1 over, which is kind of cool because that square is going to square the top. 1 squared is still 1, but it squares the bottom, which actually gets rid of the square root. So there's 2 recipes for the slope. So what are you going to see on your note sheet? You're going to see if y equals, change colors so it stands out. You're going to see if y prime equals, I'm sorry, if y equals the inverse tangent of x, then hence y prime equals just 1 over x squared. X squared plus 1 or 1 plus x squared. I don't know what I wrote in my sheet. I guess I'll just be consistent here. Write it the same. That's the nicest recipe for slope. Weird, huh? Let's just let's try to use this really quick on our original problem. Number 2 back here, weren't we saying we need the dh d theta? Let's go down, let's try to use this formula. Let's try to just use our tool that we built. Revisit. So notice this is not inverse tangent of x. This is inverse tangent of, well, junk. It's a little more complicated. So what's d theta dh in this case, or theta prime? Well, this says all you have to do is take 1 over 1 plus x squared. Notice there's the x, and there it is squared again. So for us, that's our x. So theta prime is equal to 1 over 1 plus the junk squared, right? This is not inverse tangent of x, it's inverse tangent of h over 6. And so if it's h over 6 that's in here, then it's going to be h over 6 that's in there. Right? Uh-oh, you all froze. Sorry, I saw y'all freeze, and I knew that I had left the building. So great, we just used our tool to get this right. However, notice, as I said, this is junk. This is a chain rule problem. What's the derivative of inverse tangent of junk? 1 over 1 plus junk squared times the derivative of the junk. We still have to multiply by the derivative of h over 6, which is 1/6. Because it's not just x. It's not just the inverse tangent of x. It's the inverse tangent of something uglier than x.
Are you sharing your screen?
You're seeing nothing.
Seeing your beautiful face, Doug.
How in the world can that not be enough? I don't get it. Oh, that's funny. Thank you, Faith. Do you see the chain rule in that? So what you missed just now is this 1/6. In other words, our problem is the inverse tangent of x is 1 plus 1 over x squared, but we don't have just x. We got junk. Like this is more complicated than that. So let's see, what does all of this equal? Again, for the sake of algebra practice, let's clean this up a little bit. Let's see if we can do anything to this. Let's see, I don't know. This is 1 over 1 plus h squared over 36 times 1/6. So that means the 6 gets multiplied by the bottom and the 1 gets multiplied by the top. So if I distribute the 6 to both of those, the first would get a 6, and then this one would cancel one of those 6s. And now I'm thinking, let's multiply the top and the bottom by 6 to get rid of that even more. So then I'd have 6 on the top, 36 on the bottom, and then just h squared. So to me, that's a better recipe for d theta dh. Now remember, a second ago, we used that a second ago to find, well, theta prime at 2. Let's figure out what that is. 6 over 36 plus 2 squared. That's 6 over 40. Hey, so that's the same answer we just got a minute ago. Check, that worked. What about theta prime at, what was the other one? 12, I forgot. 8, I think it was 8. Theta prime at 8, that'd be 6 over 36 plus 8 squared, which is 64. Hey, that's 6 over 100. That's the same answer we got, check. So, you know, there's kind of a practical use for this. If you have an equation that's got an inverse trig function in it and you just want to take the derivative like it is, this will do it. Your brain's probably in pain right now. I can feel your pain. Let's do a kind of like something maybe the book would give you, kind of like an example problem in the book. Let's say that y was equal to the inverse cosine, which we haven't done yet, but we're just going to look this up in the table. Except for what's the junk? Well, let's put something interesting in there. Let's not have it just be x. What do we got? Well, we got logarithm, we got exponential. Let's put something in from yesterday. What if it was like cosine of, let's say, 3 to the x power? What if it was that junk? Well, I'm looking at the formula sheet. We didn't make this one for himself, but I'm seeing that if y equals the inverse cosine of x, then y prime is equal to, I'm cheating and looking at it, it's equal to negative 1 over 1 minus x squared. Like that's the formula. Okay. So again, what I want to highlight is whatever's here goes here. All right, that's it. Simple. So for us, in green, y would be equal to negative 1, it's a constant, over the square root, 1's a constant, minus, well, our junk, 3 to the x squared. There, I did it. I'm just using the formula. But again, do you see chain rule? Like this junk is more complicated, right? I replace that, whatever junk is here, it just goes there. But chain rule says times the derivative of the junk, right? Because that's complicated. What's the derivative of 3 to the x power? Don't you find yourself looking at your note sheet like we only learned it yesterday, but I already forgot it. I'm looking at mine. What's the derivative of a to the x power? A to the x power. So it's 3 to the x power, but then times the natural log of that a value of 3. Okay, there we go. There's the derivative. I found it. And I'm lazy, but I'm not that lazy. I could at least multiply these together, right? And what about 3 to the x squared? Do you know your exponent rules? What's 3 to the x power squared? What do you do when it's a power to a power?
Add the two powers.
You multiply them. When it's 3 to the x times 3 squared, you would add them.
Oh, I wasn't.
The x to the x, you multiply them. So it'd be 3 to the 2x power if you wanted rid of the parentheses, but just leave it in there. Like there's nothing saying you have to simplify it. I mean, that looks nicer. I'd say that's worth something. So again, I view this as not terribly important because if I didn't have my note sheet in front of me, I'm going to probably erase this, but if I was staring at y equals the inverse cosine of 3x, and I thought to myself, wow, that's weird. I don't understand that. My first thing would be to do exactly what we did to make all of these in the first place, which is to change it to the cosine of y equals 3 to the x. And then I would just use the normal implicit differentiation rule. So, I mean, that was nice to sort of cheat and look at the little formula sheet, but couldn't I just say, okay, and now I'm good to go? All of a sudden it doesn't look so weird anymore. The derivative of cosine of junk is negative sine of the junk times the derivative of the junk. The derivative of 3 to the x is 3 to the x times the natural log of 3. These are things that I've learned over the course of this class. And so now I solve for y prime. Y prime equals 3 to the x times the natural log of 3 divided by negative sine of y. Done. Is that wrong? Is that wrong? No, it's not. But again, if we drew the right triangle that's referenced by the sine of y, so that we could get rid of the sine of y, if we drew, well, in one respects, we'd actually be drawing this triangle. If we drew the cosine of angle y and we put 3x in it, we could replace that. But you know, what's wrong with this? So when I say I don't think this is all that important, that's kind of what I mean. Like I might not even teach this, I guess is what I'm saying, if I didn't want to leave you, if you end up in somebody else's hands and like, you don't know how to take the derivative of inverse sine, this is something I'd be tempted to skip. I don't like note sheets. I don't like to rely. I'd rather build the tools that I need rather than buy them. Does that make sense? I built the house that I live in, for instance. That's really cool. I'm super happy that I got to do that. It's awesome to be able to build something yourself when you need it instead of just have to rely on someone else to do it. It feels good. And so, you know, the less I need some note sheet that gives me all these directions. And, you know, from your perspective, seeing this for the first time, that's hard to understand. I can get it done quickly. I mean, we got this answer. We got this green answer back here. We got it done pretty quickly. That was great. That was a cool shortcut. But, you know, I didn't even need to know any of that. I didn't need to know anything new today, and I could answer that. So, you know, what I did here in red, If I say, hey, here's this equation, take its derivative, you make one little change to it, and all of a sudden it's on your home court. You see what I'm getting at? The only thing that concerns me a little bit is, would my open math accept this answer? My guess is no, it won't. Like, it wants it with all the X's in it. So to get your assignment done, you're probably going to have to get the green answer. Probably going to have to give the green answer. But man, this is a lot to wrap your mind around, isn't it? I saw that yawn, Sydney. All right, we need to shut up. So for the next 2 days, all we're going to do is apply this to something that's really cool, but it's not easy, and it relates to what I started class with, which is how the rate of one thing affects the rate of something else. So we're actually going to take that question right there for 2 days and talk about it in more detail. And the hard part of it will be the fact that we need to write our own equation and so forth. We're just going to elaborate on that idea a little bit, and then we're going to take, as I said, 2 days to do it, and then we'll kind of work toward taking a test. So we're kind of landing the plane, but man, what a lot of stuff in chapter 3. You can see now why I broke chapter 3 into 2 parts. Can you imagine taking a chapter 3 test that was over the entire chapter? Woo. However, having said that, you're using all the stuff in this section that you learned in the previous section. So I'm only going to give questions from 3.7, 8, 9, 10, and 11 in the next test that we take, just because we only have so much time. But it involves knowing everything we've learned so far. But again, as always, I would invite you to wade into this assignment tonight, and maybe you start class tomorrow by asking me a couple of questions about it for everybody's sake and yours. As I said, I didn't look at the assignment, so I'm not sure which kind of questions it asked, but it's probably going to take kind of this approach right here. Like, that's the kinds of questions I'm guessing you're going to see. That's what mathematicians do, is make up ridiculous questions like this. All right. Stay after if you want to chat, or I will see you on the morrow.
Hey, Doug, I ended up finishing the project. Do you want us just to email it to you, or is there a place you want us to turn it in?
No, I don't care. I don't care how you get it to me. Just email it to me is great.
All right, sounds good to me.
Yep.
Hey, Doug.
Yes, sir.
I had a question about, I think I had Connor's problem as he had yesterday.
Uh-huh.
For the project. I have the function, and then I have the other function to A and H, and then the derivative, but it's not showing the tangent line. Or I have the tangent line, but it's not showing it up.
I just made you a co-host. Can you share your screen with me so we can
Yes.
troubleshoot that together?
Yep.
I'm just moving a couple things here.
Share screen.